My talk is mostly based on this work called Cosmic Tsunamis in Scalar-Tensor theories, but I like to call them waves. And I've been working with W. Inaris and W. Mota. So I'll tell you a little bit about screening and Scalar-Tensor theories in general, and then about quasi-static approximation, which has been used a lot. And if we relax the quasi-static approximation, we allow new stuff to appear, like, for instance, waves, which seems to be important in some cases. So we developed a spherically symmetric model to test Scalar-Tensor theories beyond the quasi-static approximation. I'll show you some results we had when we allowed for waves to travel in these models. And in the end, if I have time, I'll show you how waves can be generated from cosmological effects. So, as all of you know, to modify gravity, you usually start with general relativity and add some small terms. But of course, you cannot add two small terms because then it's indistinguishable from GR, and we don't want that because then you can just keep GR. However, general relativity is very well tested in the solar system. This is from the Cassini bound. The gamma parameter, which is the ratio between the two potentials, two gravitational potentials, is very close to 1 to the error of 10 to the minus 5. Which means that we need some effect to get gamma close to 1 in the solar system, and this is what's called screening. So we need theories that have screening to reduce the equations to GR in the solar system. So this is a simple way of modifying gravity, adding a scalar field to the action, right here, with the kinetic term and the potential term. But then there's also, in this case, a coupling, which we have introduced through a transformation of the matter sector, conformal, and possibly a disformal transformation, or a coupling in this case. So the conformal transformation is just a rescaling of the metric according to your scalar field somehow. And the disformal transformation, which I will not be telling you too much about, it's coupling the derivatives of the scalar field as well. So, if you do a variation of that of this action with respect to the scalar field, then you get the equations of motion for the scalar field, which is basically a Klein-Gordon equation, or Klein-Gordon-like equation. It's a damped wave equation damped with a Hagale friction, and it has got a lot of non-trivial source terms in general on the right-hand side. However, when we study this equation, usually we say that the dots are time derivatives, of course, with respect to cosmic time. We are saying that the scalar field evolves slowly with time, so we can neglect the time derivatives. And then we're left with a Poisson equation. This is good because it's a lot easier to solve, especially computationally. This can be solved faster than the Klein-Gordon, the full wave equation. However, this does not allow for the propagation of waves. In this theory, when you do the quasi-static approximation, you're basically saying, okay, we have an effective potential, which may evolve in time, And we're always putting the scalar field value to the bottom of the effective potential. So this does not allow for instance, some perturbation being spread out in the form of waves. So, okay. So we tried initially to do n-body simulations with the full equation of motion for the scalar field at each grid point in the n-body. However, we found lots of interesting results, but we were not able to understand the physics behind. So we decided to create a system which was a lot simpler. A spherically symmetric system where we should be able to test how waves and the non-static evolution of the field works in a more controlled environment. So we start with a static density distribution modeled after the Milky Way, NFW halo, and then we applied. Okay, and then we relax the field such that the field in the scalar field in the initial condition has the shape that it's supposed to have from the quasi-static approximation. In this case, it's the Symmetron field. So the value of the field is supposed to go towards the vacuum value, far away from the center of the halo. As you go closer, at the order of a couple of 10 kiloparsec from the center, then the field goes to 0 and we have screening. So we applied waves, which travel inwards. In the beginning, before the waves entered the halo, so this is a plot of gamma. Yes, so this is basically the deviation from GR. First plot shows before the wave enters. The red line, the red dotted line, is the bound from Cassini, and the green dashed line is 8 kiloparsec, which is the position of the sun in the Milky Way. So if you assume no waves, then we're well beyond, well below the Cassini limit in our case. However, as the waves arrive, we can see that they are pushing the value of the scalar field away from 0, and therefore also pushing the value of gamma away from 1. So if you thought in when you used the quasi-static approximation that the screening is valid, then maybe it's not valid if you relax the quasi-static approximation and allow waves. Yes, so the field was perturbed. However, this is of course, this depends on the frequency and the amplitude of the waves in the scalar field. So this is a plot showing just the effects somehow. If you increase the frequency or if you increase the amplitude, the deviation from general relativity increases. And the deviation can increase by several orders of magnitude compared to what you thought if you did not include waves. And this is only for the Symmetron. We expect similar things to happen in other theories as well. So in the Symmetron, it's quite easy to generate waves since we have this spontaneous symmetry break-in, where we have topological defects where in one area of the universe you have the negative potential minimum, and in other areas you have the positive potential minimum. So you get domain walls. When these collapse, you get large amounts of energy transferred directly into the scalar field. And also at the time of spontaneous symmetry breaking, I don't think we have a completely slow roll down this effective potential. So I assume that there will be some oscillations associated with this. In other scalar tensor theories, like I would expect anything, since we have a coupling between matter and the scalar field, any astrophysical process that moves a large amount of matter fast will possibly generate waves in the scalar field. What we have been looking especially at are supernova explosions. If you have a neutron star exploding into a type 1a supernova, then the neutron star completely disintegrates and spreads over a large space over a quite short time. So the density goes from being quite high to quite low in a small area, and from being quite low to quite high in other areas outside, in a very short time. So this is for the chameleon model, for instance. If you have a high density, your scalar field rests at the bottom of this potential, effective potential. However, the neutron star explodes, and the effective potential moves down really fast, and the amount of energy you have is up here. So you will have some oscillation in this area, which will spread in the form of waves. And we calculate actually in this case, if we assume that just 1% of this energy is transferred into scalar field waves, we should be able to measure this at 10 megaparsec from the supernova explosion. So it's a reasonable possibility to measure this in the chameleon model. So let me say that scalar tensor theories, they need screening, as we know. And many models, they just assume the quasi-static field when they calculate how well the screening works. I've shown that waves, at least in the Symmetron and in the chameleon case, can disrupt this screening. So for any theory, check if waves or these beyond quasi-static theories are important. So in the first order, is the screening valid at all? Maybe if it is valid, maybe we need to constrain the parameters a lot more compared to if we just assume quasi-static. And yes, in some theories, like in the Symmetron, it has been shown that waves will not affect large-scale structures a lot. However, even though the structure formation is not affected, we can still have measurable changes in, for instance, the gamma parameter or in the solar system constraints. And also, the existence of waves, for instance, can lead to new probes, new ways to detect these scalar tensor theories. That's about it. Thanks a lot.
Questions?
Yes?
So, just a curiosity. Long time ago, they were building these spherical antennas to try to detect this kind of waves, but I don't know what I
Really?
do there. Yes.
Waves in scalar fields?
Well, no, they were looking for just scalar waves. These antennas, of course, are different from the standard interferometers because they have to be and the spherical. And I'm sure that in Vietnam they were doing something like this, but then I lost track of. I was wondering if you know about it. But
No, I don't know about exactly this. Yeah, no, I don't know.
well, maybe try to dig out in the
Yes.
internet because
That sounds
I remember
really
it was a long time ago. I was doing a PhD. I'm sure that there's still something out there.
Oh, thanks.
What would be the technical complications if you consider the full equation without any quasi-static approximation?
Oh, technical, yes.
Would it be like, let's say, two waves? I mean, the wave associated to the equation itself and the wave you throw into your system. Anyway, sorry for that.
Associated with the equation itself. So what do you?
Well, that you will be dealing with the time oscillator.
Yes, yes. Oh, I see what you mean. Yeah, so in this model we tried two different things. So first we relaxed the field completely and applied external waves. Then there were no sources of waves inside. And in the other case, where we let the field be away from the static, yes, and then no external fields, and then we could measure the oscillations that were generated. So there are these two. Of course, we don't apply external waves at the same time as we have waves generated inside. That would mess up.
Could you do both? Could you consider the whole equation plus external waves?
Yes, yes, it is of course possible. So I would really like to do this on a larger scale, so it would be more like a cosmological simulation. That would be very interesting.
Any more questions? All right, let's thank Rob again.